This is a chemical fire burning violently while completely submerged underwater. You don't need a professional laboratory to manipulate the physical laws that govern your kitchen. You just need a drawer full of ordinary household junk. We are going to start with simple physical illusions, but by the end of this, we will be isolating hydrogen atoms to create a high-velocity propulsion system. Once you understand the invisible mechanics acting on the objects around you, science stops being just a boring classroom exercise and becomes a practical set of tools for manipulating your environment. Take a standard ceramic mug. If you try to drive a steel nail through the side of it with a hammer, the impact is too concentrated and the brittle material shatters instantly. But if you submerge that mug, the water provides a crucial advantage. Because water is nearly incompressible, it pushes back evenly against the glass. This support absorbs the shock and prevents cracks from propagating, allowing the nail to punch a clean hole. Liquid can also be used to introduce a counteracting force to the pull of gravity. Drop an unpeeled orange into a container, and it floats effortlessly at the surface. Looking at this cross-section, microscopic air pockets trapped inside the rind decrease the overall density, providing buoyant force. But remove the peel, and those pockets are gone. Without upward buoyancy, the dense fruit sinks straight to the bottom. You can apply this same principle of structural hacking to solid dry materials. A flat piece of paper lacks the rigidity to support even a small amount of weight. Fold that exact same piece of paper into a tight zigzag pattern, and its capacity changes. The new geometry creates vertical beams that redistribute downward load, making the flimsy material surprisingly tough. By learning how to redirect physical forces, you can make seemingly weak materials handle stresses they were never designed for. We can take this further by using chemical reactions to change how materials behave. Standard superglue is reliable, but its slow curing time can be a liability during a quick repair. This diagram illustrates what happens when you introduce baking soda to the bond. The powder acts as a catalyst, forcing the loose cyanoacrylate molecules to instantly snap together into a rigid, impenetrable lattice. The bond cures on contact. You can use a similar approach to change how a surface interacts with liquids, using nothing but the soot from a candle flame. Holding a soda can over the flame deposits a layer of microscopic carbon particles. This soot creates a textured barrier that repels water molecules, causing them to bead up and roll off without ever touching the metal itself. Chemistry allows you to do more than just mix compounds. It lets you permanently alter the physical traits of everyday objects. Manipulating structural forces and mild chemistry is relatively predictable. However, moving into high energy and combustion requires a different level of precision. That underwater sparkler from the start of the video relies on two modifications. First, a layer of nail polish provides a waterproof coating for the combustible powder, but the flame also needs to breathe. As we see in this cross-section, the sparkler contains a built-in oxidizer. As it burns, it releases its own oxygen internally, feeding the combustion reaction even when it's cut off from the atmosphere. The most extreme version of this involves building a DIY hydrogen generator to create a volatile fuel source. This setup uses raw steel razor blades suspended in a solution of water and potassium hydroxide, connected to the high amperage output of a 12-volt drill battery. When the electrical current passes through the liquid, it physically severs the atomic bonds of the water molecules. This process, electrolysis, creates separate rising bubbles of pure hydrogen and oxygen gas. By trapping this HHO gas inside a plastic bottle, you can create a highly pressurized and extremely flammable environment. When ignited, the sudden expansion of that gas creates a violent burst of pressure that rapidly propels the bottle across the room. Harnessing these elemental forces demonstrates how common household components can be reconfigured into complex, high-velocity systems. Before you attempt to replicate these experiments, it is vital to understand the real-world stakes of the forces we just manipulated. Blindly following a tutorial without understanding chemical volatility is how accidents happen. High-yield batteries and pressurized gases leave no room for error or casual guesswork. True mastery of these concepts requires a deep respect for the materials and the ability to predict exactly how a reaction will behave before you trigger it. Mastering your environment isn't about the size of your laboratory. It is about the observation and application of the invisible mechanics that govern the world around you.